Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. We were writing relationship between du by u and every other property derivative by its value. Okay, I will write down those values again once so that we can go for easy reference. This was one of them we had, and then we went to energy equation where we wrote dt by t. We had all these relations plus ds, which was, I will write it as ds by r so that it is non-dimensional again. These were the various relations we had, and we already discussed the effect of changing velocity based on this particular expression, and we found that if I had Mach number less than 1, it will go one particular direction based on these two expressions together. Okay, if I had Mach number less than 1, then ds will be greater than 0 only for one particular situation, that is du will be positive, and if Mach number is more than 1, du will be negative, that is Mach number will decrease. Du negative means Mach number will decrease. Okay, dm will also be negative. So we said that the flow has a tendency to go towards m equal to 1, that is where we stopped. And then we said we still have to use the momentum equation, which we did not use in any of these. We wrote it like this. We wrote it like this, and then we took a deviation and trying to get to one particular form in terms of fanning friction factor F. Okay, this can be written as F by 2 from as last class's definition. You can get it to this particular form. Okay, you can just rewrite it as F by 2. Once we have this as F by 2, I can rewrite this, and I am going to use fanning friction factor here, or I can use the Darcy's friction factor and put 4f instead of that, okay, whichever way you think about it. Okay, you can use one of those two numbers here. We have a relation between these two. F Darcy is equal to 4 times f fanning. This is f fanning. Okay, so there will be books which will say 4f instead of this also. Depending on which one they use, they change the numbers. Now we will start using this relation inside there and rewrite this. I want it as dp by p instead of rho u square. Okay, I previously wanted it to be du by u, so I just did this rho u square dividing. Now I want it to be dp by p because I have expression for dp by p already. Okay, so I will write it as dp first, and then I will divide the whole expression by p, with substitution of this for f by 2, minus f by 2 into 4 dx by dh multiplied by my rho u square is going to be equal to rho u du. This is the expression I have. Now I will divide this whole expression by p so that I get a dp by p here. Now I have this term rho u square by p can be written as u square by RT, p equal to rho RT. So I can now multiply and divide by gamma. So I am going to get gamma m square here. This is age old derivation, you should have done this so many times in gas dynamics anyway. Okay. Now the only difference in this particular term is rho u by p, which is equivalent to gamma m square by u. So I can rewrite the whole thing, and I will take all the terms to one side of the equation, so that it will become positive term dp by p plus that rho u du by p, I will rewrite it as gamma m square du by u. Okay. And then this one term, I do not want to cancel this 4 by 2 as 2, we will just keep it as is. So it is going to be f by 2 4 dx by dh. We will get it to this particular form. Oh, wait, I missed one, gamma m square here, gamma m square equal to 0. Okay, I took these two terms to the other side of the equation, and then I substituted this gamma m square in terms of wherever there is rho u square by p. I have done all that, and I am having this particular form. Here I have dp by p, du by u and dx. Now I want to rearrange things such that as I go along my tube, I want to find only Mach number variation, nothing else. So I want to write dp by p, du by u in terms of dm by m. Do I have that relation? I go back here, I have dp by p in terms of du by u. Okay. And that will make my expression having here dp by p in terms of du by u will mean two terms will have du by u. Now du by u I have in terms of dm by m, that is here. I just have to write all of them together inside that form. Okay. That is the next thing we are going to do. So I will write just dp by p in terms of du by u first. dp by p term happens to be minus 1 minus gamma minus 1 m square, okay, plus gamma m square. These two terms together becomes this, and the other term I will leave it as is. If you look at here, minus gamma m square and plus gamma m square will get cancelled. So I just have m square minus 1 in here finally. Du by u times m square minus 1 is the only term left. Now I will go look at here, du by u can be written in terms of dm by m if I take this bracket to the other side. So I will put that expression inside here along with this m square minus 1, write the whole thing here. So it comes out to be m square minus 1 times dm by m divided by that term in that dm by m expression plus, actually I will write it the same form we did, for f dx by dh gamma m square by 2 equal to 0. This is the expression I have. Now I want to take all the Mach number related terms to one side of the equation. So I will get it to 4f dx by dh equal to, there is a minus which I will switch over with this m square minus 1, so it becomes 1 minus m square two dm by m divided by gamma m square 1 plus gamma minus 1 by 2 m square. Okay. This is my expression. Now I just want to rearrange this this particular 2 dm by m as 2 m dm by m square. Now this 2 m dm can be written as d of m square. So this whole term becomes d of m square by m square. Now if I look at it, every term that has Mach number is all m square. So I can might as well substitute this m square is equal to some y or something and start integrating that expression. That is why I have made this thing. I am not going to do the integration here, but we will just say that it can be integrated as of now. Okay. And what will be my integral limits? This is dx, so I have to start from somewhere. I can start from x1 and go to x2 and integrate that. Then it will give me m1 going to m2, but that is not very nice. So what we will do will be, we know that given long enough distance my flow reaches m equal to 1, right, whatever we discussed already, we know that the flow has a tendency to reach m equal to 1. So what we will say is, I start with some location 1 which might be x1, or I will call that as x equal to 0. I will set, it can be any value, so I set it to be 0, x1 can be 0 also. From here I am going to go to some length x equal to L, okay, and in this time it started with m1 and ended with m equal to 1, that is what it is doing. So I am going to give these as my limits to my variables. X is going from 0 to L and I am integrating that, while m is going to go from m1 to 1. Okay, I will just do that whole thing. Instead of m1 I might as well use it as m later. I can just replace m1 with m, is just anyway a simple variable. What I start with, starting Mach number is my m1, that is all I am having. And now since it is m equal to 1, I will put a star on top of this L as is customary. We have been doing this for a long time. Okay. That says that it is the length that this flow needs to travel along this tube to become m equal to 1. This is a special length, it is not any length. Okay. We will later find that this is your maximum length that you can have. If you go beyond that, the flow will not be just doing the same thing, it will do something different. That I am supposed to discuss today's class anyway. Okay. We will get back to that. So finally, if I do all this and integrate this and get you a final expression, it is going to look like 4f L star by dh is equal to 1 minus m square by gamma m1 gamma m square. I could write it as m1 square everywhere. I just say okay, I will just replace it with m here, plus gamma plus 1 by 2 gamma natural log of gamma plus 1 m square divided by 2 times 1 plus gamma minus 1 by 2 m square. Log is on this whole thing. This is a very important relation for fan of flow, in fact the most important relation for fan of flow. Okay. Now once I have this relation, I can get other variable changes, but I will do the basic simple math way to get the other variables, which will be, I will take this dm by m and replace dm by m in terms of dx in all the other equations. Let us say I will pick this equation here, I can replace this dm by m in terms of dx now, then I will get du by u in terms of dx. Then I can get velocity as a variation as a function of x if I integrate that particular equation. Similarly, I can put that du by u in terms of x into this, I will get pressure variation as a function of dx, dp by p in terms of dx. Similarly, dt by t in terms of dx. Okay. I did not write one more here, p naught by p, dp naught by p. I will write that also right now, dp naught by p. It is not anything great. dp naught by p naught can be shown to be equal to minus ds by r. Okay. So it is just negative of the previous expression there, m square minus 1 times du by u. Okay, it's just going to come out to be this, just the previous expression negative. How do you know this? We already derived this particular thing long back. We'll just keep it the same. Since it is adiabatic, it will come out to be this. If it is not adiabatic, it may not be this simple an expression. There will be a T naught variation also. We will ignore that for now. Okay. Now, if I do all these integrations, I will get a whole set of expressions. Whatever we are interested in, I will put here. One of the most important things are P naught by P naught star. Okay. Basically, I am going to say my flow starts with a P naught and ends with a P naught star. So that is this, and during this time it goes from x equal to 0 to x equal to L star, right? And I am expressing that in terms of m. Oh, square bracket should be for the whole thing. T by T star. This is nothing great. This T by T star is just coming from T naught being constant. Simple enough expression. This comes from T by T naught, T naught by T is equal to 1 plus gamma minus 1 by 2 m square. It is coming from that formula itself, just directly. Nothing special for T by T star. P by P star. By the way, this is a similar expression as this one. I just multiplied the numerator and denominator by 2 to get to this form. It looks simpler than the previous one. Okay, and this can be obtained from this expression and your isentropic relation P naught by P. Okay, P naught by P and P naught by P star appropriately multiplied with this particular ratio to get to this. That can also be obtained. And of course, now you can find delta S from here. I do not want to go do that right now. You can go do a delta S if you want. Okay, it can be done. Okay. Typically, all these variables are listed in compressible flows tables, listed as M1 as the primary variable versus T by T star, P by P star, P naught by P naught star, 4f L star by D H, rho by rho star. This rho by rho star may not be given in all the books, but some books give this also. You can of course get rho by rho star from T by T star and P by P star. P equal to rho RT is still valid. Okay. So now we have expressions for all this. I did not write an expression for rho by rho star. I know you can get it from here. I don't need to worry about that. Okay. Now what I want to do is just go show you the plot of how things are. Okay. We will go over to the screen. If we look at this, I have plotted all the primary variables whatever we have. I am showing you here several flow parameters as a function of Mach number here. Okay, and the first one, the blue, is your F L max by D. L max is same as L star as of now. I haven't proved to you that it is L max for now. Just take it as L max for now. Okay, and what we are seeing is it is something very high when it is very low Mach number, and then that particular value drops drastically to 0 at m equal to 1, and then it goes back up again when the Mach number is higher than 1. Okay. And we know that if my Mach number is more than 1, the flow wants to go towards m equal to 1. If my Mach number is less than 1, it wants to go towards m equal to 1. Always the flow wants to go towards m equal to 1. Remember that. Okay. So, what we are finding is, if my Mach number is, let us say 0.5, it has some particular f L max by d, and if I fix my f and the d to be the same for two different comparisons, my L max is some particular value for this. Okay. If I go some Mach number closer, I find that the L max has become half, that is, in half that length it is going to be reaching m equal to 1. Okay. Mach number was changed by so much. Okay. That also says that if, let us say, the L max was 1 meter from here, this is arbitrary units, remember that. Okay. It's I am not giving correct units because f and d values are not given yet. Okay. So, if we say it is 1 meter, by the time I go from here to here, let us say this is 0.65 Mach number, by then it goes from here to here, it would have crossed half meter. It is changing Mach number very slowly while traveling long distances for subsonic case. Okay. And especially when I go very low Mach numbers, it is changing Mach number extremely slowly while it is traveling long distances. Okay. If I think about 5 meter at say 0.2, 0.3 Mach number, from there it is going to 4 meter, 3 meter, 2 meter and 1 meter. It travelled 4 meters long for that particular f by d, okay, till it became 0.5 Mach number. I started at 0.3 and it ended at 0.5 while the tube was 4 meter long. If I go 1 more meter long, it of course is going to reach Mach 1. When I go closer and closer to Mach 1, this particular flow is very sensitive to the friction. Till that time it is not. Subsonic flow, it is not at all sensitive to it. When I think about supersonic flow, when I am far away, it looks like any small change in length, or for a huge change in Mach number, let us think about it that way. For a huge change in Mach number, there is very small change in length. Okay. So, it is very, very sensitive to length in supersonic flow. Okay. Very, very sensitive to length in supersonic flow if you think about it. Okay. And when I go closer to m equal to 1, it finds that when I go from Mach 2 to Mach 1, it needs only roughly 0.3 meters. If I assume the same f by d, it is roughly 0.3 meters, it goes from Mach 2 to Mach 1. While in this case, it would have gone from, for the same height, it would have gone from roughly 0.65 or 0.7 to 1. Yeah, that is what you are seeing here. It says that subsonic flow can handle lot more length of the tube before it reaches Mach 1, while supersonic flow cannot. Okay, important statement there. Okay. What this means is, if I have a choice between my M1, the inlet Mach number of my tube, to be subsonic or supersonic, if I choose to go for very long lengths, it is better off if I go with subsonic flow than supersonic flow. Is it logical? If you think about whether it is logical, I will simply say that it is a flow through a duct with friction. If the friction is too high, then there is too much resistance. If the friction is too high, there is too much resistance. I am going to say that if I go subsonic, I am going to have lesser wall gradients of velocity. If I have lesser wall gradients of velocity, I am going to say the shear stress at the wall will be very small. Okay. Shear stress at the wall will be very small. So, I will have lesser resistance. But the same thing if it is supersonic flow, then velocities are much higher. That means the velocity gradient will be very, very, very high. If the velocity gradient is very, very high, and if my velocity profile will be more like this suddenly, instead of a subsonic flow velocity profile like this. Velocities are very high, wall velocity gradients will be very high. This is supposed to be from fluid mechanics, I am assuming you guys know fluid mechanics. So, when the wall velocity gradient is very, very high, friction will be much higher. So, friction has a huge effect when the velocity is very high, which is expected, right? It is expected from fluid mechanics anyway. So, that is the effect we are seeing here. If it is supersonic flow, I am seeing that it is very sensitive even for small distances there is huge change in Mach number. Okay. While if it is subsonic flow, even for long distances there is very little change in Mach number. Okay. Now we will go back to the plot, and when I look at the next important parameter I want to look at is P naught by P naught star. Okay. The total pressure of my flow, this is the somewhat like the net pressure energy and the kinetic energy together in the flow. You are seeing that the net energy in the flow drops as I go towards m equal to 1. I should not look at it going this way though. Okay, remember that I have to think about it going this way, because always the flow wants to reach m equal to 1. So the flow process is going to be always towards m equal to 1 from both sides. If I pick a supersonic condition, I am going to have P naught dropping from, it's all arbitrary units, right? It's let's pick if my Mach number is 2.4, it is 2 times P naught, 2.5 times P naught star, and by the time it goes to m equal to 1 from 2.4, it is dropping to equal to P naught star. But in subsonic case, of course I cannot get an exact equivalent here, there is less space, only between 0 and 1 I have values. But what we are seeing is, if I think about 0.5 Mach number jump, I am going from something like 1.3 to 1 P naught star, and I think about in here it is going to jump for the same 1.3 happening somewhere here. Okay. 1.3 P naught to 1 is happening for of the order of 1.7 or 1.75 Mach number to 1. Okay. It looks like P naught drop is a little steeper in subsonic condition than in supersonic condition if I think about the same delta m. Okay, same delta m. But of course you know that the maximum delta m possible in subsonic is 1. It cannot be just taken as is. Okay. That is also there. And one more thing I forgot to talk about is in the 4FL max by D problem, for a given L max I may have two solutions, subsonic and supersonic. Okay. Up to some Mach number only. Beyond that point, if I keep on going to very high Mach number, it is not going to ever reach FL star by D will never probably go past 1. Okay. Even if I go to Mach 20, it is not going to go past 1. Okay. So after some particular FL star by D, there is only one solution existing. Okay. And P naught, again it looks like there is two solutions, but you have to think about it as P naught is dropping from some value to P naught star. That is the way you have to look at it. Let us go for the red curve, pressure P by P star. Of course you have to again remember that the flow is going to go only up to m equal to 1. Okay. It is not going to keep on decreasing as I increase Mach number, that is wrong. Okay. If I am in subsonic, I find that the pressure decreases. If I am supersonic, the pressure increases. Is this logical? Yes, it is, because my Mach number is going to go towards m equal to 1 in both directions, and if it is subsonic, it is going to accelerate, which means my pressure and temperature should decrease. Okay. This is coming from your energy equation and momentum equation from basics. We did this in isentropic flow beginning. Okay. So the same reason, when the flow is accelerating, pressure and temperature will drop. And when I look at it from supersonic flow, it is going to decelerate to m equal to 1, so pressure and temperature will increase. They are all going in the logical direction. Okay. And density is going to be something in between this, and you know the pressure sensitivity is much more than temperature sensitivity. So density is going to do the remaining thing which compensates for P equal to RT. That is how it works. Okay. This is the case for gamma equal to 1.4 I have plotted. If I show gamma equal to 1.3, oops, maybe I have to press this. Okay. It is just almost the same curves, there is a small difference. Okay. If you notice, this was jumping slightly, the green curve and this blue curve were jumping slightly. I will go to gamma equal to 1.4, just a slight jump, not much variation. It is not very nice to look at these plots in this particular way, so I have plotted them together for various gamma values. I have plotted that 4 FL star by D as one set of curves, and P naught by P naught star as another set of curves. Blue is the highest compressibility, that is lowest gamma, and red is the lowest compressibility, highest gamma. Of course, I told you gamma is not directly related to compressibility, it is only a factor. Okay, always remember that gamma is not the only thing that decides compressibility. Okay, but it is one of the serious parameters which describes compressibility. So if I pick my f L star by d, this particular curve, we are finding that there is very little change if I think about L star variations for the same f and d. Okay. So, but there is some change. If you think about a little more compressible gas, it looks like it can manage to go a little longer. F L star by d is a little higher for the same Mach number if it is more compressible. Okay. Is that logical? Yes, it is, because it is more compressible, it can squeeze through a smaller space. So even if somebody is resisting, they will manage to go through it. Okay. When I go supersonic, I am finding same thing happening here, but it is much more drastic change here. I am going to say percentage change in L is going to be higher as I change from gamma equal to 1.67 to 1.4 to 1.3. Okay. So what is happening here, when my compressibility increases, again my L increases. If my gas is more compressible, it can manage to go a longer distance. Okay. It is just managing to go a longer distance. If I let me go to the board a little bit. If I think about this from fluid mechanics point of view, I am going to say I have some M1, let us say less than 1 condition, and I am going to say there is a boundary layer growing. I do not want to teach boundary layer in this course, but I will just tell you that boundary layer is like some blockage in the flow. It is equivalent to having a wall that is crushing inward. It is equivalent to having a wall that is crushing inward. It is giving lesser and less space available for the flow. It is equivalent to that. Of course, there is fluid moving inside the boundary layer also. I am just giving you a rough estimate. It is equivalent to something like this. So I can now think about it is like an area change problem. Subsonic flow will accelerate to m equal to 1. If it is supersonic flow, it will decelerate to m equal to 1. You can think about that, exactly same explanation. Okay. Now if it is more compressible gas, what will happen? It can squeeze more and go in through for a longer distance. Okay. That is the kind of physical feel you should have, okay, so that you can explain all these curves. Now we will go back to the remaining plots we have. If I think about compressible case, for the same Mach number, it drops a lot more, P naught drop is higher in supersonic condition, okay, compared to less compressible case. If it is more compressible, it is energy drop, P naught is much higher to go there. Okay. And in subsonic, there does not seem to be any difference, they are almost on top of each other. Okay. Just remember that if there is compressibility, there is going to be more P naught variations. Same things we saw in shock also, we will not discuss that right now. Okay. I told you that is out of scope for this course, you will just ignore it that way. Now if you look at the remaining curves, pressure, temperature and density, this I will first show this one. This is the temperature, the solid lines are the temperature, and you can see this is similar to what we will expect out of any compressible flow. More compressibility, then you are going to have temperature variation in one particular direction. This is for any adiabatic flow. We saw the similar thing even for isentropic conditions. Okay. And pressure is also doing the same thing, same as what we expected in isentropic conditions, and density will go the opposite because one is much stronger than the other. The same trend we saw even in isentropic flow curves. I will not go into more details than this, you can try and explain this by simple arguments, it will work very well. Okay. Now we will go back to the board. I want to look at this whole set of state changes in a state map. So I want to plot it in my TS diagram. TS diagram, and we know the whole flow has a constant stagnation temperature, that is my T naught here, and let us say I start subsonic, let us say this is my T1, and I am going to say it is having this particular entropy when it begins, S1. So I am going to say this is my stagnation pressure P01 and this will be my static pressure P1. Yeah, of course, I am drawing only part of the curve keeps going. This is my actual point, P1 T1 location is here, that is where I am currently, the state point. From here, if I go to some length inside my duct, what should happen? My entropy should increase and my Mach number will increase. I said it is subsonic, so Mach number will increase, which means my temperature will decrease. So I am going to go slightly lower temperature and higher entropy, that is where I am supposed to go. So it is going to go something like this, and it will keep doing this till m equal to 1, and we know that the change is much higher when I go to m equal to 1. The curve does something like this. Okay. If I want to pick a point P2 in the middle, it would have gone to some other P02 here, basically P0 dropped by some amount. From P01 it came down to a lower curve to P02, and then this will be my S2 and this will be my P2 curves. Hopefully you understand that there are so many pressure curves here, they are all going to go like exponential increase curves. I am not plotting all of them, I just plot wherever it is needed. Okay. And you can see that this is the kinetic energy component and it has increased, right. And I am going to say at this point it becomes star condition, that is m equal to 1. Now if I start with the same T0, same S value but supersonic, I may be on this particular pressure curve, P1 prime I will call it, supersonic condition for the same entropy. I will be sitting here, which will correspond to a very low T1, I will call it T1 prime. If I start here, I know in supersonic condition, of course in my along my duct my entropy increases, but my temperature will also increase. Why? My Mach number decreases. Mach number decreases, temperature increases. So I am going to go higher temperature, higher entropy. So I have to go this direction. And again we know that when I go closer to m equal to 1, the sensitivity is higher. So that particular curve looks like this. The curve looks something like this. This particular shape is what is called a Fano line. Okay, Fano line based on the person who talked about it in his analysis, Fano line, the Italian engineer called Fano. Okay. Now if you think about it, I am here, this will be my P0 star. That particular point will be my P0 star. For some particular starting condition, there will be a particular length up to which I can go and go to this particular curve. Okay. Till now we said that there is a point where things will change. Okay. What will happen if I have a duct whose length is more than the L star for that inlet Mach number? I want to start from physical field, then we will go and give math for it. Math is very easy, physical field is more important. So I am going to say I have some particular duct with a particular F and a particular DH. So, and I have a particular M1 here. I do not care it is subsonic or supersonic, both have a L star. Let us say this is my L star. This is my L star for this particular M1. Let us say I have this. If I extend this duct by some more and try to keep the same M1 in here, what should happen? That is the basic question. What will happen? I am having a Mach 1 flow here, trying to go through a duct which is going to resist the flow by friction on the walls. Like there will be a shear stress which is going to oppose the flow. What does that mean? It is going to oppose the flow means I am trying to retard the flow, I am going to slow down the flow. what should it do? It has to send a compression wave inside. Okay. If it is subsonic flow and I am sending compression waves inside, what will happen? Compression waves always travel at speed of sound. What should happen? Say I just introduced this length L, all the same it was not there, I just added this small tube extra on this. Now the flow has to go through this. From that time t equal to 0, when I added this, there is going to be a set of compression waves that is trying to go in. What will happen? They are going to go faster than this flow. They will keep on going in. What will a compression wave do to a subsonic flow when it is traveling this way? It will decrease the velocity, right? Compression waves are going to tell, don't go there, come this way along with me, right? So it is going to decrease the velocity and it will keep on going in all the way to a point where it will go to the front and change the inlet velocity here. It will go and change the inlet Mach number. So what will happen overall? My flow velocity at the inlet is going to be lesser. Okay. Density also will be adjusted accordingly based on the Mach number. Okay. And finally I am going to have a mass flow rate that is lesser. Okay. A mass flow rate that is lesser will what will be final situation. Okay. If I go back and look at my curve here, this curve comes from all those expressions we have written till now today. Okay, whatever we wrote today as the integrated expressions will finally give you this particular curve for fan line. The change in m dot will never be given by this solution, because during the solution we assumed that m dot is constant. Okay. So this is an unsteady phenomenon which I cannot express directly from any analysis which I have done till now. Unless I go to unsteady analysis, I cannot get that. We have assumed steady 1D. Okay. So when there is steady, I cannot go for this changing Mach number, changing the length of the duct kind of analysis. All I can say is it jumps to a new m dot. I will just tell you the next m dot solution. Where should it be? Can you guess? If my Mach number decreases, I had subsonic flow and my Mach number decreases, what will happen to my T1? T1 should go up, okay, but it should look a similar curve. So now I can plot one more curve on top of it, something like this. I will draw a dashed line. Something like this. So I am going to say m dot increasing this way. As I go this way, m dot increases. Going inward, m dot increases. Okay. This will be my curve. So now what happens is, if I change my L star to be a little higher, length to be higher than the L star, then the solution jumps from this curve to the higher curve such that now it is all matched it, and if I start from a lower Mach number, what happens to my L max subsonic solution? It will be higher. How do I know that? We just saw the plots, right? Plots were like this. If I decrease my Mach number, my L star increases further, f L star by d. We keep f and d constant, so L star increases. So I go to a lower Mach number as starting point. Now my L star is higher. That is the reason why the flow wants to do this. Okay, it has gone there. Okay. So now it chooses some particular curve such that it will come and make it just L star at that point. So it will go on choosing till that point. Okay. It will not go any further above. That is the idea here. And similarly, if I go to supersonic, it can do that. Now I will go back to that and look at what happens when it is supersonic flow. If I have supersonic flow and it is coming to m equal to 1, let us say here, okay, and I suddenly increased my duct length. Let us say this is my L star, m1 is now greater than 1. For a given f and dh, I have some flow, and I increase my length. What will happen? Again, there is going to be retardation of flow, so there will be compression waves going in. But it is supersonic flow. When there is a bunch of compression waves going in, they will come together and form a shock, and as it goes in, it cannot keep going in, because at some point Mach number will be higher than the Mach number of this shock. It is a moving shock. It will go and reach a point where the moving shock's Mach number will be equal to the incoming flow Mach number, and it stays there. Okay. So then I will go to a point where there will be a shock here. After that it is again 1D shock, right. So, it is going to be subsonic flow behind. Now, I have subsonic solution from here all the way to the end. If I increase the length further, what happens? One more compression or set of compression waves that travel inward, because it is again retarding. Now, it is going to go all the way up to here because it is all subsonic flow. It will come and reach this point. Now, the set of compression waves is much more strong. So, they can run against this flow a little more. It will go and stand where again the new Mach number of the shock will match the incoming flow and it will stay there. Okay. Shock would have run a little more ahead. Okay. It will go in if I increase my duct length more. And of course, if I keep on increasing the duct length, there will be a point where the shock will go sit outside this. And then I have only a pure subsonic problem inside this duct. That can also happen. Okay. Now, if I look at that in my plot, I am going to say I started with this particular solid curve and I went all the way to reach this point. Okay. But we know that from whatever supersonic Mach number, L star is not very high, right. So, what will it do? It will go this path up to some point, and then when I increase my L, it will go from some Mach number, jump to the same mass flow rate curve across here, so that it chooses a subsonic solution there. We know that above this line it is subsonic solution, right. It is subsonic solution there, and when it is subsonic solution, now suddenly my L star is very high for the same F and DH, right. I have this curve here right now. So, say I chose this particular Mach number and from here it jumped to some other very low Mach number, right. This is m equal to 1, this is my supersonic thing, this much is the supersonic limit. So, it is going to go very subsonic, it is going to be somewhere sitting there. From here it chose to go there. What happens? Suddenly my L star, instead of this being the L star, it is now here. Now, it can afford to have longer pipes, okay. But of course, it does not want to generally take a very strong shock and go, okay. It will choose only that enough shock, that much shock strength, such that it will go to a point where from here it will go and reach this point. At the end of the tube, it is going to be m equal to 1. Okay, it will choose only bare minimum. Why? I go back and explain things from here. If I extend my length of the duct by some amount, it will send only that much of compression waves till it is matching and it will go to a point where m equal to 1 at the exit. More than that, there is nothing more need to do, right. So, it will not do any more extra compression waves unnecessarily. Okay. Another way of thinking about it, if I send more compression waves, then I am decreasing my P naught further. Why will flow want to do extra work and decrease its own energy more? It will not do it. Okay. P naught will not drop any more. If I make it more strong shock than what is needed to make it m equal to 1, then P naught will drop higher. Unnecessarily, it will not want to do that. Okay. So, it will do only bare minimum. It will keep its energy safe. That is what the flow will do. Okay. So, it will go to a point where this happens. There may be a case where it may have a shock from the beginning and it will jump here, and then from here it is going to have fully subsonic solution. This is shock at the inlet. I said this is my inlet condition m equal to 1, m1 prime here. This is my supersonic Mach number. If I increase my duct length any more, then the shock will jump outside the inlet. It will be in front of the inlet, where I will still have the same Mach number. It will go there, but after that, since the shock is outside, I will draw another picture here. I will go till shock comes to the inlet. If I increase my length any more, then shock will go sit outside here, and now it is completely subsonic problem, and I am going to say length is not enough for this. What will it choose now? It will go choose a subsonic solution there. It will just jump up and go from that direction after that. Okay. What happens remaining mass flow? It came in with the same streamlines. This much of area should have gone through straight inward, but because of this bow shock sitting outside, there will be a part of the flow that will be turned out. You know, flow behind a bow shock is going to be like this. It is going to turn part of the flow out, because of which the mass flow rate inside will be lesser. So only the flow between this region will be going in now. Okay. So my mass flow rate has been decreased. This is called spillage. Okay. If you go to propulsion and you go study supersonic intakes, they will talk about spillage, and this is how spillage happens. This is one of the forms of spillage, of course. Okay. Shock comes out, and if I increase my length more, then there will be more compression waves coming out, making this shock even stronger. It will go sit more outside, which will make it more curved. So there will be more mass leaking out, more spillage. Okay. So that the net mass flow inside is even smaller. Okay. This is all just physical feel. We will go and look at how to analyze this problem numerically next class. Any other questions? Okay. See you people next time.